afternoon.
Hello.
Hello, sir. Good afternoon.
Hello, welcome back, everyone.
Good afternoon.
Good afternoon. So today we're going to continue our introductory survey of fundamental examples. Right? That's basically what we're doing now, and I hope that I'm going to start going maybe a little bit faster now, just because I would like to move on to our more systematic study. I think probably this week, between this lecture and the next, we should finish. I want to give you really the purpose of these examples is to give you a collection of examples that you use when we do general theory, right? It's very important. So dynamical systems is an abstract theory, but with all abstract theories in mathematics, it's based very much on specific examples, concrete examples, so that you have a feeling of what's going on. Okay, so if you remember, last lecture we introduced the symbolic space, sigma L plus, right? We have an alphabet with L symbols. This is the space of infinite sequences. And we had a metric. So this is a space with a metric. It's a metric space. And we looked at a map called the adding machine. And we looked a little bit at the dynamics of this map, and we saw that it has, it's minimal dynamics, right? So every orbit is dense. So today I want to introduce another map on the same space. This is a fairly flexible space. And I want to introduce a new map called the shift map. In fact, this will be, I think, much easier to understand because, as you shall see, it corresponds to something that we have quite intuitively. Shift map, and I will define it like this with a sigma. And this is defined very simply in the following way. So if we have so we have a sequence A bar, A1, A2, A3, and so on, maps to sigma of A bar equals B bar equals B1, B2, B3, and so on. And this sequence B bar, which is the image of A bar, is defined very simply by letting, okay, where BI is equal to AI plus 1 for all I greater than or equal to 1. Right? So what does that mean? That means that B1 is equal to A2. B2 is equal to A3. B4 is equal to A4, and so on, for all the infinite symbols. So what that means is that simply we drop the first term. What does this remind you of? Something very similar that we've seen already like this. You remember another map where we had almost the same mechanism? Anybody remember?
10x mod 1.
That's right. Yeah? So this is very much like when we multiplied by 10x. So in that case, we had the dot here. We had this sequence was the decimal expansion, right? And when we multiply by 10 mod 1, then we shift everything forward, and then we drop the first one because it becomes the integer term, so we get the decimal expansion is exactly the same system as this. Okay, and then we saw that we can do the same thing for 2x mod 1, 3x mod 1, as long as we use the base k representation of the numbers, right? It was basically the shift map. So, so this is really, once we've seen that, that's also one reason why it was useful to see this mechanism in a concrete case. I think it would be quite easy to understand the dynamics of this map here, right? So, for example, does this map have any fixed points?
Yes.
What are the fixed points of this?
0, 0, 0, 1, 1, 1.
Exactly, right? So it's exactly the same. So this is shift map. So the sequence that we get here is exactly the same sequence that we get here, minus the first term, right? So the terms are exactly the same. You don't actually change them. And that makes it very easy to see all the things, just like 10x mod 1 is like the model for that. And so we have fixed points, we have periodic points, right? It's very easy, just 0, 1, 0, 1, 0, 1. As long as this sequence is repeated, right, then this sequence will also be repeated. If this has a period 5 that repeats, this also will be period 5, right? It will start from a different point in the cycle, but it will be repeated with period 5. So in particular, what can we say about the topology? So the topology is a little bit different, right? So the topology, as we mentioned before, this is a Cantor set with this metric, whereas when we looked at 10x mod 1, we were looking at an interval. But remember that this topology tells us that two sequences are very close if they coincide for a large number of iterates, right? So can we, for example, prove that the periodic points are dense in this shift space? Periodic sequences are dense. Is it true? Don't fall asleep, everybody. How do we show that periodic points are dense? So we have the set periodic points of sigma, right? And suppose I take any arbitrary sequence. So let A bar equals A1, A2, A3 is some infinite arbitrary sequence in sigma L plus. How can I show that there is a periodic point? What does a periodic point mean in terms of the sequence?
If digits repeats periodically, then clearly it was periodic point. It's in the prime period equals to the length of repeating the periodic digits.
That's right. I'm not sure I heard you very well, Moksin, but I think if I understood what you said correctly, is that a sequence is periodic for this map if, as we just said, if it has a repeating block of digits, right? And of course, the number of digits that repeat is the period, okay? So how do we show that we can approximate this particular sequence with this metric by periodic points? This sequence may not be periodic, right? Because lots of sequences are not periodic. But how can we show?
Method is similar to our previous methods. Namely, now we get first k digits of this generic choice, and we can construct. Namely, we construct periodic point of prime period k. Namely, it repeats.
Exactly.
HK.
Exactly, right? So we just take the first k digits, and we construct a, for example, a number, ak, which is given by repeating the first k digits. This is obviously periodic, and this is very close to our original sequences. If we take k very large, then it will be very close, because two sequences are very close if they coincide for a large number of digits. right? So this is very simple. This is just, even though the topology of the Cantor set is different, the most important feature of this topology is that 2 points are close if they coincide for a large number of digits, and that makes it exactly intuitively the same as the real interval in some decimal expansion or base K expansion, right? 2 digits are close if they coincide for a large number of iterates. Or rather, if they coincide with a large number of iterates, then they're close, right? In the interval, the converse is not exactly true. In this case, the converse is true. But anyway, so we have a dense set of periodic points. And I think it will be easy to show that also there exists a dense orbit. How do we show that there exists a dense orbit? Remember how we did it for the 10x mod 1?
Yes, we construct an element which contains every finite combination of every length.
Exactly, right? So we do exactly the same thing here. So again, this is, once again, I am repeating it many times just to emphasize this point, that everything depends on the fact that the two sequences are close if they coincide for a large number of iterates, which is the same as 10x mod 1, and all those properties were based on this point, right? The fact that the periodic points were dense, the fact that we can easily construct dense orbits is all based on this, on the fact that all you need to approximate a point is that 2 points are close if they coincide for a large number of digits. Okay? So I will leave, it's also easy to show. I will leave this as an exercise. I will easy to show that sigma is also, so is, let me ask you, wait, is sigma bijective, injective, surjective?
It is not injective.
Why is it not injective?
It doesn't depend on the first.
Exactly. So it's not injective exactly in the same way as 10x mod 1 is not injective, right? Because obviously, if you map this sequence to this sequence, then we will have exactly L pre-images, right? Because you have L possibilities for the first digit, and all of them will map exactly to the same point. So this is exactly L to 1, right? So it's not injective, but it is clearly surjective, right? Because you can have any sequence. After the first one, you can have any possible sequence. So when you map it, you will get any possible sequence, right? So sigma surjective. Is it continuous?
Yes, it's Lipschitz continuous.
It's continuous, very good. Because if you take two nearby sequences that coincide for a large number of digits, clearly the image also will coincide. The two images will coincide for a large number of digits. It's in fact Lipschitz continuous, as you say correctly. So it's continuous. Okay, and then the various properties that we just said. So it is transitive in the sense that it contains the dense orbits, and in fact, it is mixing, right? So I will leave that for you to do as an exercise, but it's easy to see, in fact, that every open set will eventually map to the whole space, okay, which means it is mixing. I think we discussed mixing. We discussed mixing, right? Yes, okay, good. Okay, so we're going to see the shift map again in other contexts. So I think because we have spent quite a bit of time on the maps 10x mod 1, this is very similar. Unless you have any questions about this, I will move on. Are there any questions about this? Okay, you should be able to prove those properties without too many problems. Okay, so what I want to do now is move on. As I mentioned at the beginning, I think of this as kind of zero-dimensional dynamics in a loose sense because this is a Cantor set. And I will want now to talk about some one-dimensional dynamics. So by one-dimensional dynamics, I mean when X is a one-dimensional space. For example, it could be the real line, or it could be an interval, or it could be the circle, basically, right? A one-dimensional space, metric space on which we have the dynamics. So let me say that one-dimensional dynamics is a huge subject. And the fact that you are just in one dimension is not in any way, it does not seem to be almost in any way restrictive as to the incredible variety of dynamical behavior you can have. There is a whole subfield of dynamical systems that studies one-dimensional dynamics, and there is incredible richness and incredible complications and very, very deep results in one-dimensional dynamics. This is not the subject of this course, so I will only talk about a couple of very simple settings in one-dimensional dynamics, but I just wanted to say that there is much theory behind that. So I'm going to start with perhaps the simplest setting, which is when interval homeomorphism. So we're going to talk about two kinds of maps in one-dimensional dynamics. One is interval homeomorphisms. So a homeomorphism, of course, is a bijection, which is continuous on both sides. So what can an interval homeomorphism look like? So the nice thing about one-dimensional maps is that you can draw the graph, right? As we saw in the first, we didn't really draw the graphs, but maybe some of you drew the graphs of some of those maps that we looked at. So we can draw a graph of an interval. Let us suppose for simplicity that I is equal to 0, 1, but it does not have to be that at all, right? It's just easier some interval. It's always useful to draw the diagonal. So what can be the graph of an interval homeomorphism? If I draw this graph, is this a homeomorphism of the interval?
No, it was surjection. It has
Right.
to be.
It has to be surjective, right? It has to be injective and surjective. So this is surjective, but it's not injective, right? So that puts quite a lot of restrictions. One of the points about interval homeomorphism is that there's not much that can happen, although, as you shall see, a little bit more than perhaps you expect. So what does it look like? So it needs to be surjective, right? So the graph needs to map 0, 1 to 0, 1. It needs to be bijective, right?
So it must be monotonic, because continuous bijection is always monotone function.
It needs to be monotonic. That is a very good point. It needs to be monotonic. So
F0, 0, F1, 1, always.
and if it's monotonic,
maybe decreasing. Okay.
then there's not that many possibilities, right? So the image of 0, if it starts in 0, we cannot start anywhere in the middle, because then it will either go up, and if it goes up, it cannot come back down again, or it will go down, and if it goes down, it cannot come back up again. So we really need to start from 0, and it can look, for example, something like this. Right? So this is an example, a monotone map. So the monotonicity will be a property that we will use in a crucial way. It's a good observation that a homeomorphism of the interval needs to be monotone. Is there any other possibility that does not look like this?
Decreasing function, f0 equal to 1.
Very good, thank you. So the only other, so of course there's many ways that you can reach this, right? I could draw something like this, or I could draw something like this. There's many ways in which you can have this, but they all fix the endpoints. So 0 and 1 are fixed points, okay? So the only other possibilities, if you're not gonna fix the endpoints, is that you have this, something like this. So in this case, what are the endpoints doing? What is the dynamics of the two endpoints, 0 and 1?
Boundary is always preserved, so it's always periodic.
It's a periodic point. It's a periodic point. You can see it from the graph, right? Because 0 maps to 1, and 1 maps to 0. So it's a periodic point, right? Does this have a fixed point?
Yes.
It has a
Always
fixed point
there
here.
are fixed points by the Brouwer fixed point theorem or just intermediate value theorem.
But Milmukshin, also just by looking at the graph, there's a fixed point, right? By the intermediate value theorem, in this case. You don't need Brouwer's fixed point theorem here. It's true.
Much more general.
That's absolutely, that's correct, that's correct. But in this case, you don't need such general theorems, right? Some of these things you can see directly. But nevertheless, this is the good point, okay? So we have these two kinds of homeomorphism, and as Milmukshin said correctly, it's monotone. So let me write here the definition. So F is monotone if you take 2 points on the interval, y bigger than x, so there's two possibilities. If either y bigger than x implies, so this is actually, sorry, this is definition is strictly monotone. Strictly monotone. F of y is greater than f of x for all xy in I, okay, or 2, y greater than x implies that f of y is less than f of x for all xy in I. So the first one says that if you take 2 points here, x and y, and you look at the images, then f of y will still be greater than f of x, right? So if you have your function is monotone increasing, it's like this. And if it's monotone decreasing, then the order will be reversed. Right? So this will be f of x, and this will be f of y. Let me call it g, call it a different function here, okay? And a useful terminology that is we will use and will be useful for us is that we say that this is orientation preserving, and this here is orientation reversing. Okay, so what can be the dynamics? Let's look first at orientation reversing maps. Suppose we have our interval is, sorry, orientation preserving homeomorphism, right? So what can happen? We've seen that if it's orientation preserving, we must have two fixed points at the end points. Can you have one where you have more fixed points? Clearly yes, right? As long as it intersects the diagonal. For example, this one is intersecting the diagonal. This is intersecting the diagonal. Every place it intersects the diagonal is a fixed point. Can we have infinitely many fixed points?
It's the diagonal.
Identity.
Sorry?
Identity.
Identity, yes. When in doubt, try with the identity. The identity has infinitely many fixed points. We may also have something that is only the identity in some places, right? So you could have also a map, for example, that does this, and then here it goes along the diagonal for a while, and then it comes back out. So you may also have a map that coincides with the diagonal in some parts. So it may have just one fixed point here, and then uncountably infinity many fixed points here, and then another fixed point there. So there is many combinations of fixed points that it can have. Can it have any periodic points? It's orientation preserving. So let's study this systematically. Well, systematically. Let's try with one simple example. Let's kind of draw simple homeomorphism like this that has only those two periodic points. What happens to all other points?
They converge to a fixed point.
How do we know that they converge to a fixed point?
There was an exercise like this in the home.
You've already done this exercise. Did I already give you this exercise? Probably it was supposed to be an exercise to be given after this class, I'm not sure. But, so how do we know that this converges to a fixed point, right? So, first observation is that so what is special about this particular homeomorphism I drew is because it has no other fixed point, then the graph is always below the diagonal. Right? So if it has no other fixed points, then we have only two possibilities. Either the graph is always below the diagonal, or the graph is always above the diagonal.
So orbit is always monotonic sequence, so it must be converges. Any orbit is monotone.
Exactly. Very good observation. That's what I wanted to get at, right? So the fact that it's under the diagonal means that the image of the next point will be to the left, right? Because if you look at the image of x naught, you reflect it in the diagonal, this gives you x naught. This is x naught here, right? But because it's below the diagonal, that means that the image will be below. This is x1, right? And when you reflect it in the diagonal and you find it, the dynamics is happening here, right? So this is very important observation about how you use the graph of a one-dimensional map to get a feeling for the dynamics. That the dynamics is actually happening here, but you can use the diagonal to get a feeling of what's going on. So you look at the you look at the image in the graph, then you reflect in the diagonal, and this gives you x1, right? And then the graph here also is below the diagonal, so that means that the next image of x1 will have to be to the left of x1, so this is x2, right? So in this case, you will necessarily have a monotone sequence x0 greater than x1, greater than x2, greater than x3, right? And we have the orbit is the infinite sequence xn, right? So, as Milmukshin correctly said, this is a monotone sequence. Monotone sequence. And what do we know about monotone sequences? A monotone sequence, if it's bounded, it must converge, exactly, right? And this sequence is clearly bounded below by 0. It would also be bounded above by 1, right? Because it cannot go below 0. If this was unbounded, it may just go to minus infinity. But it clearly cannot go less than 0. This is a map from 0 to itself. So this is a monotone sequence, and it converges. It converges to some point P. Right, so Xn converges to P. How do we know that P is the point 0?
By continuity, P must be fixed point. We
That's
have
right.
only 2 fixed points.
That's right. So this was I guess maybe this was the exercise that Yunus was referring to. So it's, since the map is continuous, if you have a sequence whose omega limit is a single point, right, then this point has to be a fixed point. Okay, it's important because it's important to use this fact because it would seem obvious it is obvious from the picture that this is converging to 0, and it is also true that it is converging to 0, but to give a formal proof, you need to justify why it may not be converging to some point P here, right? So I'm only insisting on this just because to learn to be formally correct, because one of the things in dynamical systems is that it's very useful to draw pictures and to see things in pictures. It is essential almost to get some kind of geometrical intuition, but you must never confuse the geometrical intuition with the proof of what you're doing, right? So here, the fact that this seems to be converging to 0, to prove that, we use the fact that it converges to some point P, and then, as you correctly said, we have proved that if a sequence which is the orbit of a point, right, not any sequence, but this sequence is the actual orbit of the point, and then it converges to a point, then this point must be fixed point, okay? This implies that f of p is equal to p, and of course, the only possible fixed point is 0, so it must converge to 0. Okay, that's how you completely formally clean up this point. Very good, and so we have a similar thing if we have if it was above the diagonal, we would get exactly the same picture, but we would get a monotone increasing sequence, right? So if you started with x0 here, and then the graph is all above the diagonal, and so its image is bigger, this would be x1, you reflect it in the diagonal, which means that x1 is actually here, right? And then you go up again to the graph, and then across, and down, and then across, and over, and you converge, right? So here you get a sequence converging to the fixed point at 1. So what did we use here? We used in a crucial way the monotonicity of the orbit. Right? Now, is this always going to be true? Is it every orbit is this was a very specific case, but what if we choose now some other? not make it ambiguous here. Will the orbit of a point still be monotone?
No.
What will happen here?
Orbits may be converged to some periodic orbit. Normally, the omega limit set may be periodic orbit, or
It converges to a fixed point.
It always converges to a fixed point? Periodic orbit, what can happen? Anyone else have some ideas? Some conjectures? Some guesses? It's okay to be wrong. The mathematics works through conjectures, and then you improve your conjecture, you understand the system better, you improve your conjecture, right?
maybe it's more complicated set. Maybe omega limit set, maybe counter set is also one possibility for omega limit set.
Okay, we're keeping all the options open. I would like to hear something from other students. Have some conjecture, some idea what may happen. Could we have something more complicated? Could we just converge, or how should we, or even just how should we start thinking about it? What shall we do first to try to come to some general result about what is possible?
Try to see the direction of tangents.
The direction of what?
Tangents. Slope.
Of slope. So let's analyze this particular picture, right? Again, as I've said many times, of course, a picture is a picture, and then we need to, make some formal statement. But still, let's work with this particular picture. So this particular picture has some fixed points, right? Has some additional fixed points. So for those fixed points, we know what's going to happen. A fixed point is just a fixed point, right? So let's start by fixing the fixed points here, right? So we know that this is a fixed point. This is P0. Let's call this P1, P2, P3, and P4. So those are fixed points. So now every other initial condition will be somewhere in between the fixed points, right? So here, let's take an initial condition here.
Converge to P1.
It converges to P1. That's a good conjecture. Why do you think it converges to P1?
Because the pieces looks like the graph before.
That is a very good way to look at that, Ling. I think also, so if you look at the graph restricted to here, so, and if you notice that, of course, my picture is not very well drawn, right? Because this is not bijection, so I should have drawn it, the way I drew it was misleading. I promise I did not do it on purpose to confuse you, but the way I drew it, it was not injective because it was going up and coming back down, okay? So it is not allowed. We can draw a kind of here. We look at P1 and P2 here. Do you agree that the interval P1, P2 must be mapped by the map to itself? In other words, every point between P1 and P2 must be mapped to another point between P1 and P2. Is that true?
Yes.
Why is it true? Why could it not be mapped? Why can the graph not come down, or why can it not come up? Like
Because
this?
it's monotone.
Exactly, right? Because it's monotone. It's monotone on the whole thing, and therefore it is coming up from P0, right? And then at some point it reaches P1, and then it has to be monotone. So between P1 and P2, it is monotone. So it is strictly increasing from P1 to P2. So it can never. There's no point where it can take any value that is less than P1, and there's no point where it can take any value that is bigger than P2. This is an important point for the analysis, but it's a very simple point once you see it. But it's an important point. It's all the monotonicity, right? So we're using very much the fact. I've not stated this exactly, but in the lecture notes, it's stated as a lemma and left as an exercise, which is what Milmukshin already said, which is every homeomorphism is monotone of the interval, must be either monotone increasing or decreasing, okay? So we have this, and in which case, it's exactly as Ling said, right? So in this case, we have this picture is really just a homeomorphism of an interval with just two fixed points. It's just this fixed point and this fixed point, and it looks exactly like this. And we can repeat the same analysis here, which is that x naught, this is below the diagonal, so it will map here to some point x1, and then again and again, and it converges to P1. And what about if we take a point here? Y0 here? It's the same thing, right? Here, here also I drew, I drew the picture incorrectly because it needs to be contained inside this box. That's why the pictures, you cannot prove things with the pictures, because it's very easy to draw pictures that do not actually correspond to your assumptions, right? So that's why you have to be careful. So you always need to make sure that the picture matches your assumptions. And then here we have P1 and P2, and then here we have that it's above the diagonal, so we get exactly the similar situation where we had here, where we are moving to the right, and we converge to P3.
P2 is local repeller. The fixed point P2 is local repeller, and maybe.
Yes, of course, absolutely. Absolutely, right? So what we have here is we have that these points, P1 and P2 and P3, they are attracting, right? Because also here, if you look at this point here, then this is above the diagonal, and these points will move to P1. So P1 attracts the whole interval between P0 and P2, right? Any point between P0 and P2 will move towards P1. Its omega limit will be exactly P1. If you take a point even very close to P2, it will still be below the diagonal. The graph will be below the diagonal, so the image of that point will be to the left of the point, and therefore then it will continue to the left, but it cannot jump over, right? It cannot jump over P1 because of the fact that we said that this interval is mapped inside itself. So if you take a point between P1 and P2, it cannot jump to the other side. It needs to stay in between, but it's monotone. It keeps moving to the left, and therefore it needs to map to P1. And the same on this side. So this point is repelling because the points are moving away. This point is also repelling because the points are moving away. And this point here is attracting, right? What does this point attract? This point attracts every point in the open interval P2, P4, right? Because all the points here will converge to this, and all the points here will converge to this. This is attracting. So in this case, we have that every point converges to one of the fixed points. I will leave it as an exercise to show that this is always true. That is proposition. When F is an orientation preserving homeomorphism, omega x naught is a fixed point. Okay, for all x naught in the interval. Basically because every orbit is monotone, if you think about it, right? So because of the monotonicity, I will sketch this, but I want it to be an exercise so that you write this, but you can see that because of the monotonicity of the whole map, then if you start with any initial condition, you have two choices. Well, you have three choices. Either the point is a fixed point itself, in which case this is true, right? Because if x naught is a fixed point, then its omega limit is just itself because it's a constant sequence. Or if it's not a fixed point, it means that the graph is either below or above the diagonal, right? Because the graph at that point either intersects the diagonal, or it's above, or it's below, or it's above. There's only two choices. If it is below, then the image of that point will be to the left, right? But then you can show that because of this global monotonicity, then it cannot jump another fixed point, right? So it has to be to the left, and the diagonal will still be below, and so it has to have a sequence. You must have a monotone sequence, okay? So every orbit is a monotone sequence, and therefore it must converge to a fixed point, which also means that that's the only dynamics you can have, right? It's not an obvious thing, it's a remarkable thing. It is a kind of saying that these interval homeomorphisms are in some sense simple, that you only have fixed points, and every point that's not fixed point converges to a fixed point, right? Which means that you do not have periodic orbits, you do not have Cantor sets, you do not have dense orbits, and so on. This is for orientation preserving homeomorphisms. Okay, I think maybe I want to say a couple more things about this, but I think maybe this is a good time just for a 5-minute break. Yeah, get some water. So let's have a 5-minute break and meet again at 5 minutes to 5. Okay? See you in a minute.
Okay.
So just before the break, we finished with this realization that to some extent, orientation preserving homeomorphism of the interval are simple, in quotation marks, because the omega limit is always a fixed point. Of course, keep in mind that this does not mean that there's many different possibilities, right? Because as we said, you may have a very large number of possibilities for the fixed points, right? You may have infinitely many fixed points, for example. Can you think of a situation where you have fixed points that are not, in this particular case, these fixed points are attracting or repelling, but you may also have a situation where a fixed point is neither attracting nor repelling. Can you think of...
Maybe possible. For example, at the point P2, the graph of function just tangents to the biject, to the bisectrice, to the the graph of y2h. It's just tangent line.
Yes. I think what you're talking about is the following. So first of all, one simple case is also if you have a straight line, if you have a continuum of fixed points like in the identity, then obviously also they're not attracting or repelling, right? Because if every point in the neighborhood is a fixed point, then it's not attracting or repelling. That's a kind of trivial case. But the case that Milmukshin is saying is more interesting, and it may be, for example, it may look like this. Diagonal. So here we have P0, P1, and P2. And now we do have an additional fixed point here, but as you can see, the diagonal, because it is tangent here, right? So it has derivative 1 here, slope 1 to be tangent, then on both sides, the graph is above the diagonal, right? So what does that mean? That means that if you choose an initial condition here, it will map to the right, and it will converge to that fixed point. But if you take an initial condition, sorry, this is to the left. If you take an initial condition here, even very close to P1, the graph is again above the diagonal, so it will move to the right again, and it will converge to this fixed point. So this point P1 is attracting from one side, and it's repelling from the other side. It's okay. It can happen. Okay? And of course, you can have many situations. You can have many such points. You can have a combination. You can have some that are like that, and then you can have like that, and then any point. So you can have many different combinations. So this will motivates us to make a definition as follows. So now let's suppose, let's suppose that F is actually a C1 diffeomorphism. So in these pictures, I've actually always drawn F as a C1 diffeomorphism, right? This is, again, let me come again to the point of the danger of deducing things from the picture without actually proving them systematically, right? Using the assumptions. So the assumptions is just that the graph is a homeomorphism. And a homeomorphism does not have such a nice, smooth graph, okay? But this proposition still holds because the monotonicity, it only uses the monotonicity of the map, which holds for homeomorphism. It does not use the fact that this map needs to be differentiable in any way. So the conclusion that comes to us intuitively from the picture is actually true because we can prove it, right? Now, however, if we do assume that it's a C1 diffeomorphism, so that means that it's differentiable, C1 and the inverse is also the case, then we can talk about the derivative of the map. And then we make a definition, and we say that a fixed point P in I is called hyperbolic if the absolute value of the derivative is different from 1. Later on, I will say something about the orientation reversing case, right? In which case you may have negative slope. In the orientation preserving diffeomorphism, this will always be positive, right? So I didn't need to put the absolute value, but the definition holds also in that case. So you can see that this case corresponds to the derivative being equal to 1, right? And if it's a fixed point where the derivative is less than 1, that means that the graph must cross the diagonal, right? Because at that point, if it's a fixed point and the derivative is different from 1, it needs to cross the diagonal. It can cross it like this or like this, but it cannot be tangent. If the graph was tangent, then you'd have exactly derivative equal to 1, right? And then we have a lemma. Simple lemma that, again, I will leave as an exercise, but the lemma is that if f prime of p is less than 1, implies p is an attracting fixed point.
Just mean value theorem, continuity of f prime and mean value theorem.
That's right. You can prove it like that. Exactly. And if f prime of p is greater than 1, this implies that p is repelling, right? And this, as Milmukshin correctly says, it is quite easy to see, but again, you need to prove it, right? And the key point, so this is some point, this is the fixed point P. Okay, so if we suppose that the derivative is less than 1, then it means that it's crossing in this direction, right? Because the derivative 1 would be like this. If the derivative is less than 1, then it means it's somehow going like this. Okay, so it means that it must be above the diagonal here and below the diagonal here, right? Because if it is strictly less than 1, by the continuity of the derivative, then it must be also strictly less than 1 in some neighborhood of P on either side, and therefore here it must be above the diagonal here and below the diagonal here. It must cross the diagonal. And then it's quite easy to see that if it's below here, then you will have attracting. If it's above here, you will have attracting to here. Okay, so that's the sketch of the proof that you should fill in the details of this. And the next statement also, so let's also say that f definition, we say that f is hyperbolic if all its fixed points are hyperbolic. So the picture that I had before is not hyperbolic. If you have one point that has this point of tangency, it is not hyperbolic. But if all the points also, if you take the identity map, for example, right, if you take the identity map, if there's any piece that coincides with the diagonal, then these fixed points are not hyperbolic because the slope here is 1. Right? So all fixed points should be hyperbolic. And then it should be fairly easy to show that if f is hyperbolic, it has a finite number of fixed points. Why is that true? Why does it have why can it not have infinitely many fixed points if it's hyperbolic?
Because if it has infinitely many fixed points, then it has at least one limit point.
I could not hear the audio is not very good. You said if it had an infinite number of fixed points,
then it has a limit point. There is limit point of this fixed point. One second.
Okay, I'm going to
the,
leave.
the
Yeah.
differential, the differential of that one would be 1.
Excuse me, for some reason the audio is not so good today. I cannot hear very well. Say again, sorry.
It would have limit point, and that limit point, the differential at it would be 1.
That
Yeah,
is
well,
correct. That is correct. But that needs to be proved, of course, right?
Yeah, we take the limit with that sequence.
Yes. So this is how to prove that it would have a fixed point. If you had an infinite number of fixed points, it would have a limit point, and the derivative at that limit point cannot be hyperbolic. And why can it not be hyperbolic? So one way to see this is that you can see from the argument we just said before that every hyperbolic fixed point is isolated, right? It's either attracting or repelling, so it cannot be accumulated by other fixed points. Right? So by the continuity of the derivative, if you have a hyperbolic fixed point, then on either side you must have a neighborhood that does not contain any other fixed points, because the slope here is different from 1, so you cannot have arbitrarily close, the graph cannot re-intersect infinitely many times arbitrarily close to here, because the slope is different from 1. Right? So every hyperbolic fixed point is isolated because it's either attracting or repelling. It cannot have a sequence of limit points. So therefore, you must have a finite number of fixed points because each one is isolated. As Yunus said, if you had an infinite number, you would converge, they would have a limit, and then you can show using the continuity of the map that this limit has to be a fixed point, this accumulation point, and it cannot be hyperbolic fixed point because if it was hyperbolic, it could not be accumulation point. It could not have an accumulation points of other fixed points. Okay, so this is in some sense what I really wanted to get at in terms of orientation preserving diffeomorphism. Is that if you have diffeomorphisms, if you have this hyperbolicity assumption, so the word, some of you are already familiar with the word hyperbolicity in other contexts. It doesn't really make sense here, but it is used here for consistency with some concepts of hyperbolicity in higher dimensional dynamics, which we will look at. So this is the first example in which this concept of hyperbolicity plays an important role in simplifying the possible dynamics, right? Already is somewhat simple because we have this result of the monotonicity, but this still may have a completely crazy pattern of fixed points. You know, we may have infinitely many accumulation points and so on. And if we include this differentiability and the hyperbolicity assumptions, then suddenly it simplifies hugely. Of course, finite number might still be 10,000 fixed points, right? But it's still a finite number. And if you combine this with this, then what they mean is that there's only a finite number of omega limit points, right? So really what you're saying, and the one way to think about this is that if you have a C1 interval diffeomorphism and any initial condition, its omega limit will be one of just a finite number of possibilities, and in particular, a finite number of fixed points. This is a concept that we will come back to throughout the course. How many possible limits are there for the orbits that we consider? Even though we have an uncountable number of orbits, if we just look at the omega limits in some sense, or what they do in the limits, they may just be a finite number of possibilities. Okay, and finally for the orientation reversing case, I'm not going to say much, but I've given some exercise, but it's actually very simple. And the simple observation is that if F is orientation reversing, implies that F2, which is the second iterate of F, is orientation preserving. Right? This is very simple because the fact that F2, this is just F composed with F, right? So if you remember the definition of orientation reversing means that if y is greater than x, it implies that f of y is less than f of x. Or sorry, let me write it like this. F of x is, f of y. So orientation reversing means that if y is greater than x, then f of y is less than f of x. But then we apply f again to these two pairs. Now we have 2 points. This one is less than this one, okay? So this means that f of y is greater than f of x, right? Which means that f2 of y is greater than f2 of x, right? So F2 is also a homeomorphism, of course, because the composition of homeomorphisms is a homeomorphisms. And so everything that we've just proved, both for orientation preserving homeomorphism and diffeomorphisms, holds for F2. In particular, for example, this holds for F2. What does this mean for F?
Any orbit converges to or fixed point or periodic point of prime period 2.
Exactly, or periodic point of period 2, right? So in the orientation reversing case, we may have some periodic points of period 2. So we always have a fixed point here, but we may have, for example, you may have a point here that maps to this, and this maps to this, and this maps to this, and this maps to this. Right? So we may have a point here, Q1, Q2. And this is a periodic point of period 2. And when you take the second iterate of the map, you will see the graph, you will get an orientation preserving homeomorphism, right? Because for the second iterate of the map, if we have 0, 1, so under this map, 0 maps to 1, but 1 maps to 0, so this is also periodic point of period 2. So when you take the second iterate of the map, 0 and 1 will be fixed points, of course, because you will have an orientation preserving homeomorphism, and this orientation preserving homeomorphism will necessarily, this point will necessarily be fixed, and this point will also be fixed, this point will also be fixed. It will have at least these 3 fixed points, and you will get a similar pictures to the one we've been drawing. So depending on the derivative here, these points may be attracting or repelling or whatever, right? So remember that by the chain rule, the derivative F2 in the point Q1 is just equal to the product of the derivative in Q1 times the product times the derivative in Q2. Right? This is the chain rule. The derivative of the iterate is just the product of the derivatives along the orbit of the point. Right? So in this case, we have that this periodic, we can generalize, I've put it in the notes, so I will not write it here. We can generalize the definition of hyperbolic point to a periodic orbit. Sorry, in fact, let me spend 5 minutes on this because I think it's an interesting point. So let me write this more formally. So definition, a general definition, okay, for one-dimensional maps. In this case, notice that you can never have periodic points of period 3, for example, right? Because all the periodic points you get become fixed points when you take F2, right? Because when you take F2, this is orientation preserving, so we know that this can only have fixed points, it cannot have anything any other periodic points of any kind. So it means that in the orientation reversing case, you can only have one fixed point, and you may have many period 2 periodic points, right? But let me make this definition more in general. So if P is periodic of period K, of period K, of minimal period K greater than or equal to 1, because we include the fixed points, is a special case of periodic points. So we say that P is hyperbolic if Fk prime of P is different from 1. So in other words, it's hyperbolic if it is hyperbolic as a fixed point of Fk. This coincides with the definition. So if P is hyperbolic of is a periodic of period K, then it's a fixed point for Fk. Okay. Now notice that in general, if P is a periodic point, there are several points in the period, like in this case, okay? So this point Q1 is hyperbolic if the product of these is different from 1. So is it possible that the product is different from 1, but one of these two is equal to 1?
Yes.
Exactly, right? It's possible. So you may have that the product is different from 1, which makes the point hyperbolic, but it may be that if you look at this point, I say actually, okay, this one is -1, but so I look at what I want is the absolute value, right? So maybe I say, but look, here the slope is exactly -1, so this periodic point is not hyperbolic. It doesn't matter that the slope here is -1. What matters is the product along the orbit. And similarly, but more seriously, you may have that the derivative in both of these is different from 1, but the product is equal to 1. Right? So you may have, by chance, that this here is like 2, and here, or here it's 1/2, and here it's 2. If the derivative here is 1/2, is different from 1, the derivative here is 2, which is different from 1, but the product of 1/2 and 1, 1/2 and 2 is 1. Okay? And so the total derivative along the orbit would be equal to 1 in that case. Right? This is an important point to visualize, is that when you have a periodic orbit, because we will use this concept of hyperbolicity in some other situations, it's really this. It is as a fixed point of the periodic, of the iterate of the map. Right? So if you just look at the derivative along the orbit, it doesn't tell you anything, because you need to look at the product, and that's the only thing that matters.
So, Professor, is that F2 prime?
In this case, F2 prime. Thank you. Yes. Thank you. Thank you, of course, yes. Okay, so I think I've done what I wanted to say about interval homeomorphism and diffeomorphism. As you see, the dynamics is to a large extent describable. This is an example of a situation in one-dimensional dynamics where we can describe the dynamics. So I want to just before we finish, I want to give two examples in one-dimensional dynamics, and the other example I just do not want to go too much into it because it's a generalization of what we've already seen, but I would prefer to do it now instead of leave it till the next lecture, because I don't want to say that much about it. So the second class of examples I want to talk about is full branch maps. And full branch maps we've already seen. So by full branch maps, I mean, for example, 2x mod 1, or I mean another map where you may have for example, we divide the interval into 4 parts, and then each part, it does not have to have constant derivative. It might map to this, it might map like this, it might map like this, it might map like this. So I will now give the exact definition of full branch maps, but what we mean is that we have a partition of our interval into subintervals, and each subinterval maps bijectively or is with a homeomorphism or even a diffeomorphism to the whole interval. Okay, so let me write the definition here. Definition, so f from I to I. Let me see just how I formulate it here. Yes, fi to I is full branch if there exists partition P of I into subintervals such that for each subinterval in this partition, F restricted. So when you construct these partitions, as we shall see, there's always a bit of an issue as to whether they're closed or open subintervals. It's a bit annoying because sometimes you want them to be closed subintervals, sometimes you want to be open subintervals, and sometimes they cannot all be closed or open, and so we kind of don't worry about that too much. Right? I'm going to write the definition that is strictly correct, but usually we don't worry so much about what happens at these boundaries of these elements. So now I will say that I will make the condition on the interior, f restricted to the interior of omega, that maps the interior of omega to the interior of the interval I, right? So I'm just to make it formally correct, I'm going to say that this interior of this interval maps to the interior of the whole interval is a bijection. And then sometimes we're interested if this bijection is actually a homeomorphism or a diffeomorphism. So we say that f is piecewise C0 or C1 or C2 or affine or whatever it is, right? If f restricted to the interior of omega has the corresponding regularity, right? Is a homeomorphism or C1 diffeo or C2 diffeo, or it's affine, in other words, has constant derivative, or affine, right? So these are the possibilities. Well, it could be C3, or it could be Lipschitz. Okay, just the regularity. So we say that f is piecewise Lipschitz if each of these, if this, for every omega in the partition, this is Lipschitz or Hölder, whatever you want to say. Okay, this is the definition of a full branch maps. Now, full branch maps play a very, very important role. Even though they're very special maps, they play a very important role because they have very good properties, they have very interesting dynamics, as we saw for 10x mod 1 or 2x mod 1. They have a very rich dynamics in some cases, but also they can be used to study other systems, as perhaps we shall see later in the course. So the only thing really I wanted to give here is this definition. And is there some questions?
Is this for only one subintervals or for all subintervals?
For all subintervals, right? Yes, so we say that f is piecewise C0 if this is homeomorphism for every interval. It's just terminology, right? So we will be interested to know that it's the regularity of the map, but of course, in general, the map globally may be discontinuous. The reason why we're giving this definition is because we may have something like this, where the boundaries of the partitions, the map may be discontinuous, right? But we don't worry about that. We just have full branch maps on each element of the partition. It should map the interior bijectively, say, as a C1 diffeomorphism, for example, to the interior of the whole thing, right? And these are obvious examples, right? So example 10x mod 1, this is 2x mod 1, is an example of this. So this you know, you can just draw the graph, you can draw for intervals, they don't have to have the same size, there can be other sizes. But the reason why it's called full branch is because this is a bijection, right? This is the reason why it's called full branch, because you may imagine a map that's like this, right? Where this interval here is mapped to the whole thing, and this interval here is only mapped partially. This is not full branch, right? So the full branch property is really focusing on this, and this is just a way of describing the regularity of the map on each branch. So can someone tell me if you think we may have a full branch map with infinite number of branches?
A decreasing sequence of partition. There are half 1 and 1/4. We can define, I think.
How's that?
Simple example is just 1/2 from its half interval after 1/4 interval. We divide each time.
Yeah, that's correct. So it's clear that we can easily construct one. We just define an infinite. We just divide the interval into an infinite number of subintervals. We just take the interval and divide it into an infinite number of subintervals. The easiest one is if you just have an infinite number converging to this. Like you said, this could be whatever, 1/2, 1/4, but just any one. And then on each one, you could even have this map to be piecewise affine even, right? On each subinterval, you can do something like this, and you get a piecewise affine full branch map with an infinite number of intervals. There is also a very famous map, which again we're going to study a little later on, which is very interesting, which is called the Gauss map. So the Gauss map is the map f of x equals 1 over x mod 1. And if you think a little bit about what it does on the unit interval, this is mod 1, so So we're looking at values of x between 0 and 1. Right? So if you take values of x between 0 and 1, then 1 over x will always be bigger than 1. Right? If you start with x between 0 and 1, 1 over x will be bigger than 1. And I'm not going to take you through it, but you should make sure that you think about it a little bit. But it's not that difficult to see that this interval 1/2 to 1. Okay, one interesting way to draw the graph of this map is to think about the graph of the map 1 over x. Wait, so yeah, so 1 over x, in x, 1 over x goes like this, from 0 to 1. This is the graph of the map 1 over x, right? So when you take mod 1, what does that mean that you take mod 1? So if you look at 0, 1, so the part of the graph that interests us is this part here. So here we have the point 2, 3, 4, right? So where is it that this point here is 2? What point does it correspond to, where 1 over x is equal to 2?
1 over 2.
Exactly, right? So 1/2. Okay, so what does it mean that we've taken mod 1? So now when we take the image of this map for all the points between 1/2 and 1, what we're doing is we take a point x here, and we look at the value 1 over x, and then we take mod 1. Now what does mod 1 mean? Mod 1 means you're taking the fractional part, the decimal part of the number, right? So all these numbers here will be between 1 and 2. Right? So the fractional part will be simply how far up it is above 1, right? So if you take this point here and you see the value of 1 over x, right, then the fractional part will be this distance here, right? So as you take points between 0 and 1, you see that if you take a point very close to 1, right, then the fractional part will be very small, close to 0. So when you take a point x that's very close to 1, you will get a point that is also very close to 1, right? And as you get very close to 1/2, you will be up here, so you will get a value that is very close to 1. Sorry, maybe I said wrong. This is to 0. So anyway, the conclusion is that what you're doing is you're really taking a copy of this graph and just shifting it down, right? So you're taking this piece of graph and you're just translating it down, because every time you're translating down by 1 unit, because every time you take a point here, you look at its image, what you're interested in is in this distance here, which is exactly the distance you get here if you just shift the graph down. Does that make sense?
Yes.
Yes. And then you do the same thing here. So between 2 and 3, right? So this point here corresponds obviously to 1/3, right? And then you see now that if you take any point between 1/3 and 2, it will map to here, right? And when you take the fractional part mod 1, what do you mean? You just take the fractional part, which means you're looking at the distance above the point 2, right? So if you take this point here, then you see that it goes to here. And so really what you're doing is you're shifting this down, but by 2 this time, right? And you get this, and so on. And you continue doing it. And so the result of all that will be here that you have 1/3, 1/4, 1/5. Of course, I'm not drawing it very correctly, but then you have the picture looks something like this, and then here it will look something like this, so on. So imagine that you're going, basically when you come here, you are going way, way up there, and you're picking up the graph there, and you're translating it down. Okay, so here you have 1/5, 1/n, and you're getting closer and closer to 0. Notice that 0 is not the boundary of any of these partition elements, right? 0 is accumulated by the partition elements, but 0 itself does not belong to the boundary of any of these partition elements. So we have these partition elements are between 1/2 and 1, right? So the partition elements, In, are basically of the form 1/n, 1/n plus 1, or 1/n plus 1, 1/n. Okay, 1/2 to 1, 1/3 to 2, and so on. And on each element of the partition, it is a diffeomorphism. A bijection, which is a diffeomorphism. So from the open interval, 1/3, 1/2, it maps exactly diffeomorphically to the open interval, 0, 1. Right, so this is a full branch map. This is perhaps the only or the most simplest full branch, infinite full branch maps that's given by an explicit formula. This is interesting when we have an explicit formula because we can calculate some things explicitly, but of course, if you now take this same map and you just change it a little bit, so instead of drawing this, right, you just change a little bit the map. You can keep the same partition, or you can even change the partition a little bit. Then you get another full branch map with an infinite partition that is not 1/x, but it's still a full branch map. Okay, so clearly there's infinitely many possible full branch maps with finite partition and with infinite partition. So something that unfortunately we do not have time to do because it would take me a little while, but if you're interested, you can investigate, is that this Gauss map, Gauss was interested in this map for a particular reason. Does anyone know why?
Distribution, maybe.
Excuse me?
What about distribution?
So, no, I'm not sure I heard correctly, but one of the reasons he was interested is because this has, you can use this map to give a very interesting, different representation of all the real numbers, right? So as we saw in 2x mod 1, 3x mod 1, 10x mod 1, they are naturally related to the representation of numbers, decimal representation, base 2, base 3, and so on. So in these numbers, if you take a point here and you look at its orbit, in fact, under this map, it will always belong to one of these partition elements. And it turns out that if you keep track of which partition elements it belongs to, you can reconstruct, you can code, in some sense, this point by the orbit, and you get something called the continued fraction representation of real numbers. I'm not sure if you've heard of that or not. If you're interested in this, you can look it up. There is something called the continued fraction representations. Continued fraction representation of real numbers, where you write x as 1 plus 1 or 2 whatever, 3 plus something, 5 over 2 plus, and then you have a kind of a fraction on the fractions, okay? And it turns out that this is naturally related. If you write the continuous fraction representation, then it gives you the coding of the dynamics of a point exactly in this map. But this is not, I just wanted to give it to you so you know, but we will not, this is not part of the course because we do not have time. So the only thing that I did want to say about full branch maps that is very important is, what can you tell me about the iterates of a full branch map? So what can you tell me if F is a full branch map? What can you tell me about F2? So let's look at the simple example where F has 2 branches, right? The simplest example. But let's not make it too easy and make the branches the same. Let's make the 2 branches a little bit different. So let's suppose this is 0, 1.
I think the number of branches multiplying square two times. If it's n, then number of branches is n squared for F2.
So will it still be a full branch map? Okay, this is once you see it, this is very simple, but it takes a little while to get your mind. And this is a very important property of full branch maps, which we're going to use later. So I want to finish with this, but I want to make sure that I emphasize that you should really play with this. Okay, what I'm just going to say now, you should play with it until you feel completely comfortable with that. So let's take the diagonal here. So let's call these two, say I0 and I1. These 2 partitions, let me call this a point P. So what does the second iterate of F, what is it going to look like? Well, the first iterate maps I0 to the whole interval. Right? So it maps I0 to the whole interval, which means that some part of I0 will map back into I0 itself, and some part of I0 will map to I1. Right? So here, this is the point P, this is I0, this is I1, okay? So on the y-axis, so this means that here we have this splits into 2 parts. This interval here is going to map bijectively to I0 itself, and this interval here is going to map bijectively to I1. So if this interval here maps to I0, what is the second image of this subinterval going to do?
0, 0.
It's going to map to everything, right? Because I0 maps this subinterval of I0 is going to map bijectively to I0, and then when you apply again, it's going to map onto the whole interval. It's going to map to the whole interval. Whereas this interval here is going to map bijectively to I1, and then the next iterate is going to take I1 and map bijectively to everything, right? And the same thing is going to happen here. We divide into 2 pieces like this, and they have the same property, right? So this one will now map bijectively to I0. So this maps bijectively to I0, and then it maps to everything. and this one maps bijectively to I1, right? And then it maps to everything. So we will have exactly 4 intervals, right? So here we have the point P. Here we have those 2 subintervals. One is here and one is here. Here we have these other 2, all right? And then under the second iterate of the map, this, after one iterate, maps to I0, and then it maps to everything. So this will map to everything, and the same thing, this one, because this one maps bijectively to I1 and then to everything. So it maps to everything, and the same for the other 2. Okay? That a grunt of satisfaction and understanding. So you can see that you can now repeat this again, right? So now you have this original point P was here. This is I0. This is I1, right? And so now this little interval, again, after the second iterate, it will subdivide it into 2 bits. One of these will map bijectively to I0. This one will map bijectively to I1. And so after, scusa, sto finendo, 2 minuti. Sì, 2 minuti e finisco, scusami. Okay, I have to finish, sorry. So this maps bijectively to I0, and then therefore, when you apply F again, it will map bijectively to everything, right? So each of these we can now divide into 2. Each of these subintervals we divide into 2, right? So we had now 4 subintervals. Each one we divide into 2, and each one of these maps bijectively to one of the original intervals, and therefore when you apply F once again, it will map to everything, right? So under F3 will again be a full branch map, right? You will divide again into these intervals, and each one will map bijectively. Okay, so this takes a little bit of playing around, but this holds even for the Gauss map, right? You do not need just 2 intervals. So in the Gauss map, you have these same, if you draw the diagonal, you have these intervals, right? And if you look at each one of these, this interval here, maps bijectively onto everything, which means that you can define a partition here such that each element maps to one of the elements of the original partition, right? Because this maps to everything. So there is a subpartition of this where each one maps to the original element, and then at the next iteration it will map to the full branch, right? So you can easily construct, you need to divide each of these elements into an infinite number of subintervals, and that will give you a partition for F2 of the Gauss map, and F2 will still be a full branch map. It will still have infinite number of partitions, but in this case, it will be a much more complicated infinite partition because you will have accumulation points inside each one of these intervals. You will have an infinite elements of partition, and then infinite here, and then infinite here. That's what F2 will look like. But it still will be a countable partition of the element, of the interval. Okay? So this was really what I wanted to say about full branch maps. So we're not going to study the dynamics because we will do that later. For the moment, I just wanted to give you the definition and to emphasize this particular point, the fact that every iterate of a full branch map is a full branch map. And I very much encourage you to play around with this with 2 or 3 branches to get a feeling, because this will play a very important role in what we're going to do later. Okay, I'm sorry I went a little bit over. Thank you so much. See you on Friday.
Thank you, Professor.
Okay.